Good. Yeah, so since you asked, it is good to start from there. Like I'll reach this step, but in the next step, in 2 steps, right? So this is equal to like do the gradient thing, right? So this is d cube r. D cube r is the total gradient. F of r times g of r. And then minus of this, right? That should be clear. And then the question is, oh, how do you get this, right? And if you notice, d cube r, that's a volume, right? That's a volume element. It can be written as whatever area is perpendicular to this particular derivative, right? dA. So volume has 2, this is 2, right? dA has 2 of them, right? Times that is, let's say, what should I call this? dl, right? And this is a very special choice, and yeah, that's it. And this dl in this coordinate system, A and L, gradient is actually L hat, right? Times d by dl. So these two exactly cancel out, and whatever is remaining is what you get here. Is that clear? Right? There's a little more specialty in here. There is some coordinate system I have chosen here, but that's the details I'm missing here. So this is not as, like I've hand waved this if you want to say, but it should give you a clear picture of what's happening. Like there's a volume, there's an area, and a surface. Okay, so yeah, why did I do that? Yeah, because I want to do this. I want to do this differentiation by parts on this integral, right? So there is a gradient here. I want to bring it to the other side, right? But it'll give me a boundary down there, right? So when I bring the gradient on the other side, that's this term, but it comes at the price of a boundary term. Okay, okay. So let's see. So let me. Integrate it. So this is minus d cube r, or let's say area, right? So this is dA dotted with a boundary term. So this is dA dotted with gradient. Let me write this slightly differently. Let me write the same d cube r. This is the volume. This is the first term. Think of it this as this term here. And that is the next term will be plus, right? I switch sign. D cube r gradient of g of r minus r prime, acting only on g, dotted with gradient of phi, which is equal to, let me expand this out. So this is d cube r, and this let me write this as a rho of r divided by 4 pi epsilon naught r minus r prime. With me? This is actually a surface term, right? Because of this idea. This is actually a surface term. This survives only on the infinite part of our universe, right? And we require that the electric potential is zero. Remember that always we have boundary conditions for our fields. We require the electric potential to be zero on the surface of our universe, let us say. Right. So, but here that's not just what we're looking. We're going to say the derivative of the electric potential is also zero. That means the electric field is zero. Right. So that's one. But now we want to put in one more thing. Right. So I'm going to do one more step here. So that's equal to, let me write this, minus d cube r. I'm just going to copy this down. It survives only on the boundary. And now let me do one more. So that is, first I moved one of the derivative onto the right side. Now I move the second derivative also on the g, right? Earlier it was acting on phi, I'm moving it to the g. But then there is another differentiation by parts I have to do. There is another boundary, correct? So that's a second boundary there, but this time with a positive sign. It's d cube r. So that's gradient. Or you can say divergence, right? So this is of the gradient of g and phi of r. And eventually minus of d cube r of gradient square of g. Is that clear? All the steps? Any questions? Okay, okay. But basically, just to give you, I mean, if it's not clear. I have only integrated by parts. I've done it 2 times, that's all. Okay. And each time I did, I got this extra terms there. What is this term in the curly brackets? What is that equal to? Huh? Right, that's delta function, correct? So if I include the minus term, that's a delta function. And the moment it's a delta function, what's the integral?
1.
Integral is 1 if there is nothing else. If there is a function, it's a function itself, correct? So this integral is doable now, right? Because it's a delta function, this one. Right? This is a delta function, actually minus delta function, r minus r prime. Right? So what is this integral equal to? D cube r delta cube r minus r prime of f of r. What is that equal to?
F of r prime.
F of r prime. The delta function is a very simple integral to do. I just have to see when this is equal to 0. Replace all the r's with r primes. Replace all the r's with r primes. That's it, right? And that makes this very simple to do. Right? It's just phi of r prime. Right? And so let me do that. So if I start with this term now, I have phi of r prime is equal to d cube r charge density rho of r over 4 pi epsilon naught r minus r prime. Right? That's these 2 terms, and these 2 terms I'll write it on the right side. So this is plus EQR. It's only on the boundary. It's only on the boundary. So it's G. Let me write it in a symbolic manner. Gradient of phi minus gradient of phi, gradient of G times phi. That's what it is. One should write r minus r prime everything, but I think that's details. Is that clear?
Yeah.
Okay. If, only if, right? If phi is equal to 0 and gradient of phi is equal to 0 at the boundary, S, right? So this whole thing will survive only on this S. If it is 0 on S, then I have prime equal to QR usually we say R, so let me swap R and R prime. It doesn't matter really. Let's swap R and R prime. Wherever I see an R prime, I will say R. And wherever I see an R prime, I will say this is. And this swapping doesn't really matter. So that's okay. And that's your solution. If you give me a charge density, if you do this integral, you get the electric potential. Is this a familiar idea? Yes, it is a familiar idea. Let's say if you have charges Q1 at position R1, there is another charge Q2 at position R2, and then there is charge Q3 at position R3, and so on. If there are n charges, what's the electric potential due to that? So the electric potential at position R is equal sum of all of them, right? So you sum of I going from let's say 1 to n of Qi over 4 pi epsilon naught times R minus Ri. And that's what you do. If it is discrete charges, that's very clear. Right? That's the superposition principle. If it's a continuous charge distribution, you have to replace the summation with integral. So if it's a continuous charge distribution, this gets replaced with d cube r, wherever Ri is there. So this gets replaced with Ri, right? And Q gets replaced with, because now there is a volume integral, right? So Qi gets replaced with rho of R, Ri, which is exactly what you get here. Right. So this is, so the idea is that this is nothing but your superposition principle, which is the Green's function, right? So this is the Green's function. So if you want to say it in this form, this is the Green's function of rho of prime and over epsilon naught. Yes.
So you keep referencing like the boundary. Could you, so I thought that we were like looking at like infinite empty space with the charged, with one like particle.
Yeah.
I think I missed exactly where you brought in these boundary terms. If you could show.
Yeah, so for example, let us say, in this case, this is a trivial scenario where I don't have any boundary. Basically, the boundary is at infinity. Okay. A simple example could be that I have a conductor at z equal to 0. A perfect conductor, let's say, which has this requirement that electric field has to be all perpendicular to that, right? And now let me say there is a positive charge in front of it, right? Now this is not 0. So these two terms that I dropped completely does not get dropped in this in the presence of a conductor. Then I will work them out, right? And then put in the boundary conditions, what my boundary conditions. And this is like we solved quantum mechanics problem, right? We have a boundary condition and we have to solve for it. That's a little work, which is what leads to what you call the method of images. It's very beautiful when you actually really solve for this Green's function, and then you write the solution. Oh, this is nothing but a method of images. If I were to imagine that there is another negative charge here, that does the job. So its analogy is there, but actually mathematically it comes out. So you can actually solve the differential equation. It's a little laborious there, laborious in the sense it takes about a few pages to do it, but then it's like the understanding is very straightforward. It's a differential equation, solve it and get it. Right? Here, the boundary condition here would be, you would say this is a conductor, right? So on the conductor, phi has to be a constant, right? And the electric field has to be 0. So gradient of phi has to be. So those are the few conditions you would put in. You can put in any voltage you want on the conductor, but typically you say it's 0 volts just for simplicity, and then phi is 0 gradient up. Then again, it gives you the same apparently. Maybe, yeah, in this case, maybe this really doesn't contribute even in this case. I'm not sure. Yeah, no, this is not correct, right? So electric field, this electric field, so this, yeah, this is not correct. So electric field, only one component goes away, right? So the parallel component of the electric field is 0, but this component is so. So this is, how do you say, dotted with, let's say this is Z direction. Z dotted with the electric field is special. Is that clear what I said? Like the electric field all has to come perpendicular to the conductor, right? What's the definition of a conductor? The conductor is that electric field cannot be inside the conductor, electric field is 0, right? But it can come perpendicular. Like the moment I go here, electric field is 0. But here, electric field has to come perpendicular. That is right before it, it's that. So on the boundary, what is happening? This is the electric field dotted with Z. So whatever is Z in this direction, there is no electric field. So that's the boundary conditions. That it is slightly different from this. This is a total electric field. That's and then you have to again work it out. But it's a one-dimensional problem. It comes out very easily, but we will not go there. Like that's another like first semester we have done that. It's kind of a nice little exercise. It's like in quantum mechanics, you solve a boundary value problem and you get a solution. It's exactly that. Here, this is for a conductor. There is another problem one can see, and that is that it doesn't have to be a perfect conductor, right? It could be an epsilon 1 here and epsilon 2 here. So that it could be an interface, right? And I say dielectric function epsilon 1 and epsilon 2, but that's pretty much saying refractive index 1 and refractive index 2. Correct. So remember that refractive index is very roughly speaking, it is square root of epsilon. I say roughly speaking. Any idea why I said that? That's because epsilon actually has a real and an imaginary part. Epsilon is not a real quantity. And why is that? Because we talk in terms of the frequency space. In the position space, refractive index is real, but we usually measure the refractive index in the frequency space. We talk about refractive index of red light, refractive index of violet light. Right? So it's a frequency dependent thing. And the moment you go to Fourier space, it can be measured. Right? It's a complex term. And this is the real part. So then this is the real part. In that sense, that was not completely. But now if you think of it like this, and then now this is not even equal to 0, right? So there could be, so there is an electric field here. There could be an electric field here also. But one can actually see this very clearly, and this is what happens during reflection. So there is an electric field here. And think of it as light itself, like it's not really light. So let's say this is the electric field. So this is the electric field at this point here. Imagine this, so there's some electric field here. There is a direction of the electric field in the plane, and there is a direction of the electric field perpendicular to that. So there's a component parallel to the plane, a component perpendicular to that. The requirement is that whatever is epsilon 1 times the electric field perpendicular to that. So I'll call that perpendicular 1 has to be balanced. This is perpendicular. So by that I mean this is perpendicular. And this is parallel. Okay. So the perpendicular components has to be better. This has to be satisfied. This is because of Gauss's rule. And the other pieces, so this is one parallel has to be exactly equal to parallel. Now what happens in that case is that if this is the electric field, E parallel has to remain the same, but if epsilon 1 is larger and then epsilon 2, that means electric field has to be smaller, right? It is the inverse of this. So if epsilon 2 is greater than epsilon 1, epsilon 2 is greater, that means this has to be less. So when I go, the moment I go there, this decreases. Like this is the electric field in here. So this now decreases, so decrease it. This. So now notice this has decreased. So suddenly the electric field that was coming in, it will move a little bit. And that's what happens with light. The light actually, when it is reflecting or refracting, it bends because of the small change in the electric field. This is a detailed scenario where you're seeing the electric field. Typically, we say that's Snell's law, right? Snell's law, we say that light bends, but it is the electric field that is satisfying the boundary condition obeyed by Gauss's law. Just Maxwell's equations are governing that. And it is this boundary conditions that is happening. But those are the details. I was avoiding the boundary altogether. I was trying to motivate that, okay, the electric potential is given in terms of G. And G is just 1 over R. Right? Clear? Right. Again, we have that's your Laplacian. The moment you get this equation, I can think of this equation. Right? And once I know this equation, I can write phi. And let me now, now that we have done this in detail, let me now motivate this in a slightly different form. So this is gradient square of phi is equal to rho over epsilon naught, right? That's also our equation. And there is a second equation I wrote. Now I this time write symbolically. Gradient square times G is equal to a delta function. And delta function is in many ways just the identity. In what sense is it that identity? If I were to have a matrix, right? Ij. Right? This is a canonical delta. This is equal to 1 if I is not equal to j. Sorry, if I is equal to j, and 0 if I is not equal to j. And the delta function also has very similar properties. It's equal to infinite if r is equal to r prime, and 0 if r is not equal to r prime. And if I think of it as a continuous variable I in j, then delta function in some sense is a generalization of a Kronecker delta. This is a matrix, a finite dimensional matrix. And delta function is in a sense an infinite dimensional matrix with a continuous variable. Right? It has its own challenges because convergence and other things comes into picture, but in that spirit, I'm saying this is 1. This is an identity matrix, right? In that sense, this is 1. If you think of it like that, what is G? This is an operator, multiplying on that gives you 1. So what is L square equal to? That's, sorry, so let's say inverse of this is equal to G. Right? So what is Green's function? So I just gave you an interpretation of Green's function. That's the electric potential due to a point charge. But now coming symbolically in a mathematical language, if I have an operator multiplying on something and giving you something, this inverse of this operator is the Green's function. Okay. So if that's the Green's function, now I use this here, I use that in there. So phi now is equal to gradient square inverse of rho over epsilon naught. Right? Symbolically speaking, this is all differential equations. So when I invert a differential equation, I get integrals, right? But symbolically speaking, that's G. That's nothing but G times rho over epsilon naught. But then you realize that, oh, these are differential equations. I don't simply write G, so there's an integral that comes in. When I'm inverting that, I get an integral. And that's exactly what we saw there, right? So phi is integral of G times rho. So whenever there is any differential equation, I'm making a bigger, like this is a power of Green's function. Whenever I have a different non-homogeneous, inhomogeneous differential equation, if it's homogeneous, then it's easy. Whenever I have an inhomogeneous differential equation, I try to find the inverse of that operator, that is the Green's function, and the solution will simply be the Green's function multiplied by this. With the features of boundary and all coming into details, that's the idea of Green's function. And this will be always true. Yes.
So the Green's function is inverse of the operator.
Correct.
Yeah, so the last line, I get it, you get the G and rho and but how can you get the integral?
Okay. That's because this symbolic nature has that integral inbuilt. So what am I? Okay, so let's go back to this. And so that's why it is symbolic, right? This is del square of G of R comma R prime. So there is an I and a J. If I think of it as a matrix, there is an I and a J. That's I and this is a J. This is operating only on the I. I still have to keep the J open. And that is what you're getting by integral. So how am I releasing that? So let me try to explain it this way. Maybe let me try, okay? Okay. If you have yes, I think I should do it like this. Okay, yes. Think of it in the following way. If I have an operator M times N is equal to 1, right? Let me say this is I, and let's say this is K. That's K, that's J, and that's I and the J. Right? So notice K is summed here. Right? That's a matrix multiplication coming in. Now when I have to invert it, so this is a summation, right? So this whole thing is a sum. So even though what I'm trying to say here is that in principle there is a K here, right? Which we don't write when we say M N is equal to 1. When I'm saying M N equal to 1, there is a summation over K inbuilt in them. So now when I say N is equal to M inverse, let's say this is M N is equal to A, right? A. So this is A. I have to go to the other side. It is in this way of doing it, I have done M inverse, right? But now I put in the integral back. Right? So when I write it in this form, so this will be Nij will be equal to M inverse, right? M inverse of I, K, and then A, K, J, and then I have put in that summation back. And that's what that integral is doing, if that helps you.
Yeah.
Right? And so, like symbolically, we are suppressing the integral and then bringing it out back in the detail. But this is only an idea, right? It doesn't help much. This is very symbolic, but this gives you a power in the sense that if whenever you have this sort of equations, which is coming everywhere, it doesn't have to be ENM or anything. You're doing some modeling of a black hole and you get this equation. How do you solve it? Solve for this, and then just invert it. That's a standard mathematical trick that you use, and Green's function is a technique you use to solve second order differential equations. And there are details, of course, there's a boundary and all that. Like when you get into details, all those details are there. But broadly, this is all what we are doing. If that is true, then this should all be applicable to 150 already. I didn't realize that. Oh, we just did this. It takes time. Okay, in 2 minutes, at least I can motivate it. It's not anything. Let's see. Yeah, magnetostatics, correct? Yeah. So it should be. Can it be done as simple as this? So let me, in 2 minutes, do magnetostatics. So that's your del cross J, right? What did we do here? Since it was curl free, you got this. But now this is divergence free. If the divergence of a vector is 0, what can you say about the vector? Huh?
Like it has no source.
Yeah, that's correct. It doesn't have any source. That's an interpretation. But here, curl free made it that there is a potential, scalar potential.
It will make a vector potential.
Yes, it will make it a vector potential, and not just a vector.
Curl of a vector.
Curl of a vector. So this this allows you to write the magnetic field in this form, and that's called the vector potential. Just because it is source free. If that's the case, I can put this back in there. Now I'm solving for A, not for phi. I'm solving for A, right? And then you say this del cross A is equal to mu naught J. Right? That seems to be a complicated equation. No, it's not, because I can do one more thing, and that this is equal to minus del square of A, and that is a del of del dot A. That's an identity. Okay, from here to that. And it is possible to choose an A. You choose a gauge. Okay, so this you choose a gauge. Oops, I should change. You choose a gauge which is del dot A is equal to 0. Okay, that's a detail. Again, one can talk a lot about what is a gauge and so on. But if you accept that it is possible to choose that, this goes away. And you get square times A or is equal to mu naught. That should be very familiar. Why is it familiar? Same operator. Right? So same Green's function. I don't have to do anything. Like it's exactly the same solution. So I don't do anything. I just immediately write down the solution. Same superposition principle. Do the integral. Instead of an epsilon, I write mu naught this time. Right? In the numerator, there is d cube r prime and mu naught over 4 pi and j of r over r minus r prime. So that's it. one-to-one correspondence, except I have replaced the charge density with the current density, scalar potential with the vector potential. Same ideas go through, except now it's current, it's a vector quantity, you're adding vectors. So you gotta be careful there, but those are details. It's the same superposition principle. Same Green's function. Yes.
So when you have the r minus r prime there, that was from the fact that you knew the solution
Exactly.
was, okay.
Yeah, this is the Green's function, right?
Right.
1/4 times this is the Green's function. And there it was epsilon naught in the denominator. Here mu naught is on top. So this is the source. That's the same idea.
Just real quick note. So it is like common in like the literature and stuff, or at least possible that the Green's function will be some delta of r minus r prime. It could be a different delta function.
Delta function is always the same, right? What do you mean by that?
Like the delta function could be like dependent on even like another variable, for instance.
Another variable. I think what you mean is that there's always a point. See, the idea is that charge density is being broken into point.
Yeah.
Right. So I want a point source. Usually a differential equation deals with an inhomogeneous term. This is a function of r. I say that let me keep the function only at one point.
Okay.
Is that clear?
Yeah.
Let me get the solution for one point, and then I'll add up all the points. If I keep the general enough, I just have to add up all those points. That's the idea we're using with Green's function. Is that clear? The answer is I don't think so. Yeah. What we are going to do now is, okay, electrostatics over, magnetostatics over in 2 lectures. We want to really bring in the dynamics, right? And the Green's function for dynamics is slightly different, small difference. And that's where relativity will also show up.
So the Green function is actually helping me in a way that I don't have to solve the second order differential equation.
That's how I have presented it because it's a review, right? In the first semester, I will solve for the Green function. And I will solve it again here, but I'll solve for the bigger Green function. I'll solve for the time dependent Green function. But you will have this small Green function sitting all the way there. If I put t equal to 0, I will have that normal Green function sitting there all the time. So it will be clear. And then let's say we won't get there right away. Before that, we will do some conservation principles. Let's go to the dynamics first. Work with Maxwell's equations a lot, and then talk about Green's functions. Because dynamics is hard to work with. There are very less solved problems there, except you make approximations. So one of the approximation we will make is that we are interested in the solutions at infinity, which is what is radiation. So there is a source here, but I won't be interested in close by. I'll go very far. Then the solutions becomes can be solved. But complete solution is hard in this case. Like electrostatics itself, you saw that it gets hard very quickly. There are only special cases of sphere and plane. That's the only 2 solvable problems. Actually, cylinder also. Now, electrostatics, there are lots of solutions here. But in dynamics, it's only the sphere and a plane. Not even a cylinder is solved. Only sphere and a plane get solved. We'll see how much I can go in there. Yeah. You have a class at 2, right? So you should make it stop on it.
It's literally right across the hall. Yeah,
Okay,
it's in
okay.
the modern law. Thank you.